So this focuses on structural analysis, and in particular, it's qualitative structural engineering. So we're going to see how we could do analysis without using a computer. So we get a feel for the output we should expect. This is the idea. Before you use a computer to do analysis, you really should have a feel for what answers are expected. So we'll begin with a recap from Seminar 1, for the benefit who weren't at Seminar 1 a couple of weeks ago. Then talk about what's the problem with computers. V&V is verification and validation. And the pros and cons of two-dimensional analysis versus three-dimensional analysis. And then we'll look into some behavior of frames and so on, how we decompose them. Eventually, we'll get on to the self-assessment exercise by way of the technique. But by way of background, this isn't my invention. Qualitative structural engineering was promoted and pioneered by Dr. David Braun when he was at Bristol Polytechnic many years ago. And the cover shown there is the cover of his book, Understanding Structural Analysis, which goes, I'm going to touch on some of the subjects on the methods of qualitative structural analysis. He goes into a lot more detail with this. The book is available on Amazon. You can get it for free if you're an Amazon Prime member in an electronic version. Unfortunately, if you want the hard copy, paper edition, it's about $130 available on there. But if this is a new field for you, frame analysis and structural analysis, certainly worth a look at. What he also did was take this concept and put it into computers. And so he developed computer software called QSE, Qualitative Structural Engineering, which is no longer available. But at the time, it was very, very useful because it's one of the most intuitive pieces of software I've ever come across. It had a drag and drop interface for frames. But of course, like all good software companies, he got bought out. So, reminder of seminar number 1. So don't forget that materials are not homogeneous nor azeotropic, but we usually assume that they are. Members rarely meet at a single point, but we usually assume that they do, particularly for analysis purposes. Loads rarely apply uniformly, but we usually assume that they do. So we cannot predict with any real accuracy what loads are going to be applied to our structure, how the structure will respond to those loads, how the materials will behave or perform. So we use a simplified representation, i.e. a model for analysis and design. And to recap from the statement that O. Barrett made in the 1980s, engineering is not a science. So what we do is take those scientific laws and by means of an art, we synthesize those solutions, whether they're good, bad, or indifferent. And that's the creative side of engineering, which involves imagination. So when we're doing assessments, structural assessments on existing buildings, engineering judgment plays an even bigger role than in new design, because half the time you don't know what you've got and you don't know what you're dealing with. You've got to make some judgment, some, shall we say, assumptions. So usually when you're looking at an existing building, and we'll get into this in a future lecture, we have little information about the material properties that we used. So we may have to test the material properties, and it's quite difficult to tear the building apart once it's being built. So different engineers will come up with different solutions depending on their approach. So as a rule, if one approach gives twice the capacity of the other, one of those approaches might be wrong. Now, generally, engineers err on the side of caution and normally take a conservative approach, especially when it comes to existing buildings. So that's where the deviation may come. But if there's a massive difference, if there's an order of magnitude difference, then there's something incorrect in one of their approaches to the assessment. So it's not an exact science, especially seismic assessments. But the trouble is, all those magic numbers make those analyses look scientific. So even response spectrum and time history analysis, they're all approximations and they use simplifying assumptions. And don't forget that earthquakes are unpredictable and each earthquake is unique. We assume that the structure is loaded in an orthogonal direction, usually ignoring the vertical seismic actions, happily ignoring the fact that the load is dynamic and it's reciprocal and acts about 6 degrees of freedom at the same time. So it's a bit like gravity acting on six directions at once, and that gets very complicated and variable. So what's wrong with computers? Well, the trouble is the people using the computer don't necessarily have enough structural engineering knowledge to carry out the task they've been given. It's often a graduate who's plonked straight onto a computer with a piece of software they don't really know much about to assess a task they don't really know much about. So don't forget, engineering design is very different from analysis. The other downside of computers is there could be quite a difference between what the originator of the program intended and what the designer who's using the program actually is trying to do. So always keep in mind, are you analyzing the right thing? Is the program being used out of context or beyond its scope? So don't forget, every piece of software has scope and it has limitations to its scope. And sometimes some of them will not tell you that it's being used out of scope. The good ones will. And the checking process is very difficult. Sometimes when you're presenting with a whole pile of computer output, it's very difficult to tell whether it's actually correct or not. And it's not obvious for a user, even an experienced user. They may not see the weaknesses in that program. And believe me, every computer software will have weaknesses in the analysis and in the way it's been programmed and the way information is contained, processed, and represented as analysis results. So I'm going to borrow from David Braun again. He stood up at an international conference, being the man he is, and said what engineers really need is a crap detector. So when you're presented with a whole heap of output from a computer, you've always got to be able to look at it and go, no, that's a load of crap. And there's two sides of this computer thing. One is validation. So are we modeling the structure correctly? I.e., do the numbers add up? Has it been debugged properly? And then the other side is verification. Are we modeling the correct structure? Are the nodes and elements used in the analysis really representative of the connections and members in the structure? Are the restraints representative of the real boundary conditions? So we'll come on to that. There's an imaginary boundary conditions, and there's real boundary conditions, and then there's what we analyze and represent in the computer. So the validation part is down to the software engineer. But the other half is really down to the structural engineer in this case. A little word about two-dimensional analysis versus three-dimensional analysis. Now, an awful lot of frames, particularly ones we're dealing with from a day-to-day basis, could be adequately analyzed in 2 dimensions, based on the simple concept that most buildings are rectangular. So, obvious advantage, 2D modeling is much simpler than 3D modeling, much quicker to generate your model and much easier to interpret the results. It allows rationalization and repetition in the real structure. So if you are simplifying a structure, you can repeat it and repeat it again. And that's where economy comes into your building. It also means that you have economy in your design process. Yeah, don't forget about out of plane behavior. So if you're analyzing your two-dimensional portal frame, it also needs to be restrained out of plane. And then if you suddenly model it as 3 dimensions, you'll find there are torsional effects you've forgotten about and out of plane behavior that you've forgotten about as well. So, and most standard profiles, particularly steel profiles, are intended primarily for bending about one axis. So an I-beam is designed to be a floor beam. It's an I shape, and it's primarily designed to be bent about its major axis. So we come on to understanding structural behavior. So it goes back to geometry and calculus and algebra, if you remember all that. A qualitative approach uses a much broader and more intuitive and dynamic reasoning to evaluate the behavior of any particular structure. So what are the key principles in understanding this? Well, you needed to consider the deformed shape of the structure. So how is it going to behave under load? To reduce complex structures into statically determinate simple structures from which the true structure may be rebuilt. So you're probably aware that statically indeterminate structures are actually quite difficult to understand, and doing numerical methods by hand for statically indeterminate structures is long and laborious. I mean, the advance of computers means it's relatively quick and simple these days. But once you've got the output from the computer, you need to know what it really means. So one aspect is consider the structural form, particularly in two directions at least. So what are the primary structural elements? You know, how do you put the main frame together? And these are going to be transferring the horizontal and vertical loads to the foundations. But those primary structural elements carry secondary structural elements, such as secondary beams and purlins, girts, cladding, and so on. So they transfer the load from the outside to those primary structural elements. And then there's other elements such as the cladding itself, and partitions, and those are really only transferring loads to the primary and secondary structural elements as well. So this is where you begin to decompose the structure. And here's a typical steel-framed, steel-clad warehouse type structure. And it's fairly obvious from that where the main structural elements are, if only all buildings were as simple as that. So you can take a complete building and chop it up into primary and secondary elements, and then you can, from that, derive your primary members and generate frames for analysis. And in some cases, elements will be represented as loads that are imposed on your primary members. Okay, don't forget the effects of wind. Obviously, that's going to be one of the load cases you've got to consider in all directions. Generally, we'll consider it in the along direction and the across direction as well. But thanks to symmetry, we can simplify the analysis to that. I'll be coming back to wind analysis and how you derive wind loads for 1170 in a later seminar. And where does the resistance and lateral loading come from? Well, these are your frames. You've got portal action in the across direction, in the transverse direction, and then you've got bracing here in your longitudinal direction. So you need to consider both. You also need to consider how it gets from the end wall to your bracing. So effectively, you're making a little truss there with your bracing. Some hints as to things to consider. Obviously, you need to consider stability. So there's an overall equilibrium to consider in a building. And so tall, slender buildings are more likely to be unstable than short, squat buildings. And then you can derive simple models for some of your elements. In a basic sense, vertical loads, you've got gravity coming down, it's got to get into your ground, your foundations. It's your structure is in between and your structure is carrying that load and dispersing it down to the foundations. Similarly with the lateral load, you've got to take it from the walls and take it down either bracing or shear walls and take it down into the foundations and thereby into the ground. Not forget that. So modelling of frames, so completely pin-ended, and if it wasn't for the diagonal, this frame would be a mechanism. Nice simple braced frame. And we can start adding 2 more joints. You've got a little more stiffness in there, which means smaller deflection. 4 rigid joints means much stiffer and much less deflection. And if you look at this as a sway frame, the 4 stiff joints will sway less than the 2 stiff joints. But there's a price to pay for that, which is the complexity in your foundations and your base connections. So what I would tend to say is try to avoid rigid bases, because that means your foundation has to carry that moment too. Slender columns. So your slender column will be governed by the geometry rather than the material strength of the component of that column. And so you're looking at buckling, and you're looking at Euler buckling for that. Similarly with short or squat columns, the capacity will depend on the material properties rather than more than the geometry. So what about these boundary conditions? Well, they're supports, they're restraints. And so the simplest case is a simply supported beam, you've got pin ends. And increasing stiffness, if we build in the ends, you can reduce the stiffness, but of course you're transferring bending moments into your supports. And looking over the columns, again, pin-ended, it's going to have the longest effective length of, if you've got 2 ends. The longest effective length will, of course, be a cantilever. And in simple terms, now the codes will give you slightly different values for those numbers in terms of effective length factors, depending on the material. They don't always go for a cantilever as being 2L, but it's basically like half a simply supported beam. And so the technique of qualitative structural analysis, and this you will need if you're going to approach the homework. So the first is to determine the points of certainty. So first of all, which points stay in the same place, and then which points are most likely to move under loads. Consider the movement under the loads. Draw the direction of the support reactions. So sometimes it's fairly easy, sometimes it's a bit more complicated because of the shape of the frame and the direction of the loading. So consider the rotation at the supports. So obviously if it's fixed, you will have a rotation at the support of the member connecting to that fixed support. Draw the deflected shape, both based upon all of those points. Determine the tension side of the structure and draw the shape of the bending moment diagram on the tension side of the structure. Now that is a typical convention, is to draw the bending moment as positive on the tension side of the structure. Other engineers do it the other way around as well. It kind of makes a bit more sense if you do it on the tension side. We'll see a bit later in a minute. So here's your first example. It's simply a small frame with 2 elements and a built-in support. So this is a rigid joint. This is free. And we've got 2 loads, one vertical going down and one horizontal going across. So where are the points of certainty? We've got a point of certainty there, that's the support. Chances are the load will go down at that point B, so therefore the frame will go down at that point B. And because you've got a load coming in from the side, point D is likely to come in as well. Draw the deflected shape. So we've got the reactions in. You've got a vertical reaction there due to this vertical load. You've got a horizontal reaction here due to this horizontal load. And because you've got a rigid support, you'll have a moment. Wherever you've got a rigid support, you'll have a moment there. So join the dots, basically, and you can draw a deflected shape as shown in red. So we draw the tension side of the structure. In this case, tension, 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 all down there. And then you can draw the bending moment diagram on the tension side of the structure. So this is your first point of reference. Here is a point, that's a little cantilever. So your moment will be 0 there, and it will be bigger than 0 here. That then flips around to the next stage. There is no load between there and there, and therefore the moment stays constant. We've now got a load, so therefore the moment increases as we get to the support. So the moment is a maximum at the support. Example 2, a simple frame with a column and a beam. The column has a rigid base and the beam is on rollers. So the points of certainty, at point A, that's staying where it is, that's not moving. The load is likely to push the beam down. Now C is a bit more complicated. It can't go up and down, but because the beam is moving, then the roller is either going to go to the left or to the right. And because we've got a rigid joint there, that is likely to rotate because of this load coming down. So we draw the deflected shape and add on the reactions. And again, don't forget, we've got a rigid base, so therefore we've got a moment. And the reason it's a bit hard to grasp at first, why does the roller go to the right? Well, simply because this load goes down, and that load will push it down that way. That load is pushing or pulling section B inwards. So which is the tension side of the structure? Well, we can see it here. Again, it's on the top, on the side, and we've got some tension underneath. Sorry. Let's draw the bending moment diagram. So you've got basically a propped cantilever with a rigid joint at this end and a prop at this end. You've got the sagging moment due to the load, and then you've got the reaction moment here as well. Obviously, this is a pin, therefore the moment is 0. There's no other interaction here, so therefore that flips around there to the other side. There's no other load down here, so this is straight. And because this is straight, you're looking at single curvature. Slightly more complicated example 3. Again, 2 beams and a column. 1 pin-based support and 1 roller support and 1 rigid support. So what do we do? Well, we need to look at the points of certainty. Ooh. So the support is a point of certainty. Ooh. The load moves downwards, as it should do. Again, the roller support will either go to the left or to the right. We're not quite sure which yet, but it's not going to go down or up. And the other point of certainty is down here at the support. Okay, so where's the rotation? Well, because of the load here, that is wanting to bend down in there. And because that bends down, this effectively bends up. And because this effectively has a reaction here, this pulls this beam back down again. And the whole of that is turning B. Because that turns B, this column bows out this way because of that. Obviously, the deformations are exaggerating here. So that's why we can draw the deflected shape in that direction. So determine the tension side. So the tension is going to be on the underside, under the load because of the sagging, and then on the upper side next to the support because of the hogging. Now here's a funny thing. There is no load between there and there until you get there. So therefore that is uniform and coming down to zero. Because it's a pin support, pin on a roller, the moment has to be zero. Similarly, this is a pin support, so the moment has to be zero. So the combination of that and that will equal that. Now we can argue, and it will be dependent on the stiffness of the beam to the column, how much each takes. But this is the driver of that moment, and that stiffness, the relative stiffness of the beam and the column, will determine the distribution of the moment to each. Okay, now a little tricky one. Example 4. It's a continuous beam, but we've got a moment applied. Now, this is the case where you have a stair sat on a beam, a secondary beam, and the secondary beam is then suspended on a longitudinal primary beam. So consider the points of certainty. Obviously the supports, A, B, C, D. Now, only A is fixed, so B, C, and D can move side to side, but not up and down. Now we consider the movement of the structure under the load. So what's going to happen? What you're doing is you're applying a turning force here. So that little blob is going to rotate anti-clockwise, which means the beam is going to be deflecting down. But you've got a reaction here pushing it back up to meet this support. And similarly, you have a reaction here pulling it down to meet that support. Okay, okay, okay. So far, so good. Then what happens? Well, there's no other loads applied. There's only reactions. So you've got the two vertical reactions here because this wants to come down, but this is pushing it back up. And similarly, this is heading on up until it gets pushed down by the reaction here as well. So all of these need to be in equilibrium. So the vertical downward reactions match the vertical upward reactions. So from that, we've got our starting points for the deflected shape. And then we draw the deflected shape. And then we put on the tension side. And then we can put on the bending moment diagram. So the big one is here. That's where the moment is applied, and then that's distributed. Now, if this was a pin, it'd be zero, but it's not a pin, it's continuous. So this is like a continuous beam with a cantilever edge, if you like, and that's picking up this reaction. And because you've got a reaction here and a reaction here, that is putting in effectively double curvature bending. And then we're back to single curvature bending as well. So here we've got double curvature bending. Then we have single curvature bending one way, and then single curvature bending the other way. So the self-assessment exercise, and there are 20 questions. Number 4 you may spot, and number 8 you may spot. The first 10 are beams, and then the second 10 are frames. Now, for those in Redco, it's already on the common drive undergraduate seminars. For those coming in from the outside, if you put your email in the chat, I will send you these, and I'll quite happily mark them up for you. But that brings this seminar to an end, and I'll open it up to questions, and the questions can be based on the seminar or anything else for that matter.